to thank the organizers for the invitation. It's a great pleasure to be here for this Poema workshop, and I'd like to thank you all for coming, and I hope this will be a nice last talk of the day. So my talk today is based on a joint paper with Daniel Plaumann and Stefan Weiss, and so the topic is also closely related to Daniel's topic, so you will see hyperbolic polynomials again and spectrahedra. So this theorem is about the numerical range. This is a thing that I believe comes maybe from physics. Anyway, here's what it is. So suppose you have a d by d complex matrix A. Then I just define this set. This is the numerical range. And so you take all unit vectors in C to the D, and then you do x bar transpose. So you transpose, you have a row vector and you complex conjugate every entry times A times X. So this produces a complex number, and you collect all of these complex numbers as X ranges over all unit vectors in C to the D. Okay, so you get a subset of the complex plane that we will be mostly interested in. We will later generalize this also. So let's maybe look at some basic properties of this set. So first of all, it contains all of the eigenvalues of the matrix A. So why is that? Well, you just choose as X a normalized eigenvector corresponding to this eigenvalue. So A times X becomes lambda X, and X bar transpose times X becomes 1. So you get lambda as an element of WA if you take X to be a corresponding eigenvector. Of course, if the matrix happens to be a Hermitian matrix, so A bar transpose equal A, then you get a real number if you compute this. And actually, that's equivalent. So one direction is easy. If A is Hermitian, then the numerical range of this matrix will be a subset of the real line in the complex plane. The reverse implication is not as trivial. So I've put this here as an indication that this numerical range retains some information about the matrix. For instance, also, if A is normal, so if it commutes with its adjoint, then W of A happens to be a polytope, namely the convex hull of the eigenvalues. So when I say convex hull, I think of the complex plane as R2, and I take the convex hull in this Euclidean space R2, of course. Okay. So let's see an example. So usually this is not a polytope. So even in this very simple example of this complex matrix that has in fact integer entries, almost all of which are 0, we get a numerical range that looks like this. So we will see this picture again. I've plotted here on the right the numerical range for this matrix. This is this yellow region in the complex plane. And we will see, what this blue boundary of this numerical range is and how to compute it for this example. So first, the fact you might have noticed that this yellow set is convex. That is in fact not a coincidence, but always true. So that is a theorem that goes back to Toeplitz and Hausdorff in 1919. No matter which complex D by D matrix that you take, the numerical range of one matrix is always a convex subset of the complex plane. It's a non-trivial theorem. It's very nice. Fact that will fail in higher dimensions for the generalizations that we will consider. Okay, so let's try to connect this to things that Daniel was talking about. So first is a simple trick that every moment person knows very well. So if you have a complex matrix A and a complex vector X, then we are interested in forming X star AX. So now I write X star for the complex conjugate transpose vector. And of course, X star AX is the trace of X star AX because this is a 1 by 1 matrix. X star AX, but within the trace, we can cyclically permute. So I can move this x star over to the other side. Okay. And so this is the same as trace A x star, and that's usually, that's an inner product on the set of complex matrices, or it's a bilinear form. I'm not sure why my connection is not so good, but I hope you can still see. Okay. So with this trick, once you can see the slide, okay. With this trick, we can give a different representation of the numerical range. So the first thing here is the definition that I've rewritten using this trick. So instead of writing x star ax, I've written A times x, where x is a Hermitian matrix of rank 1. So that means it's of the form x star or x star. And the trace being 1 corresponds to the condition that the norm of this complex vector is equal to 1. Because the sum of the diagonal entries will exactly be the sum of xi bar. Okay, so this is sort of really the definition rewritten with this observation on the top of the slide. And then I'm using, so next I want to drop this constraint that the rank of the matrix is equal to 1. And I can just drop this constraint because I know by the Toeplitz-Hausdorff theorem that the numerical range, this set is convex. So I know that the convex hull of the rank 1 Hermitian matrices of trace 1 is the set of all PSD Hermitian matrices of trace 1. So I can just drop this condition because convexity, because of the convexity of W of A. So what have I done? I've written the numerical range here as a linear projection, right? This is a linear projection from the space of Hermitian matrices of trace 1. And the numerical range is the image of the now compact set of Hermitian matrices that are positive semi-definite and have trace 1. So the numerical range is the projection of a spectrahedron, right? A Hermitian spectrahedron. So I think that came up in Daniel's talk as well. So usually that's defined for symmetric ones, but for Hermitian ones, it's basically the same. Okay. So I have a spectrahedral representation of every numerical range. Essentially, the only things I've used are the definition and the Toeplitz-Hausdorff theorem. Otherwise, I would have maybe here, for this equality, I would have had to take the convex hull of the left-hand side. Okay, so in our example, we can write this down. And in order to do this, I want to write this pairing A comma X. I want to write this as a projection in a more explicit way. And in order to do that, I form, in some sense, this is still called real and imaginary part of A, but it's now with respect to this Hermitian form on complex matrices. So the real part of a matrix is not, the real part of every entry for me, but it is 1/2 of A plus A star. So A transpose complex conjugate. So for this example, if you do this, you get this 4x4 matrix up here. This I will call the real part of the matrix, and the imaginary part, I analogously, I do 1/2i times A minus A star, and I get this matrix. And now I can write this in real coordinates, right? Now I can write this map, take AX for every Hermitian X that's PSD and has trace 1 in real coordinates like this. So take a second to appear, it seems. There we are. So the numerical range is, you take this product form, this is trace of real part A X star. And this projection, this will now give you real numbers because A, so real part of A and imaginary part of A, they are both Hermitian matrices, and you pair it with a Hermitian matrix. So this will give you a real number. And this is just another way to write down the numerical range directly in real coordinates instead of this right? This here is equal, this is equal to AX as a complex number. Okay. So far so good. So I can also see the chat. If you want to type a question, I'll try to take a look, and so maybe I can also answer in real time. So let's move on maybe to Kippenhahn's theorem that appeared on the title. So this is named after Rudolf Kippenhahn. I put his dates here because he recently died. He died about 2 weeks ago. Got his PhD in Erlangen in math, actually, with Specht, that some people know, some Specht modules, for example. But he then moved on to become a physicist. He was at the Max Planck Institute for Astrophysics. But this topic here was his math PhD, essentially. So what was his point of view? Well, he said the numerical range, maybe we should look at the polar convex body. And this is where we're headed. So we still have our fixed complex matrix, size d by d, A, with its numerical range, but now we sort of want to look at the dual picture. So from this A, we form two things. First of all, we form this polynomial, this determinantal polynomial from the real and imaginary part, as I defined it on the previous slide. So this will be a homogeneous polynomial in the variables x0, x1, x2. Will be of degree d, and it will have real coefficients because the matrices appearing here are Hermitian. And in fact, you know, this is a determinantal polynomial. This is a definite representation because here I put the identity matrix. So this is a hyperbolic polynomial, and it describes a spectrahedral cone in R3. And this is essentially the spectrahedron that I'm interested in, S of A. So this is the section of the cone corresponding to P for x0 equal to 1. So in this plane, x0 equal to 1 in R3, I get the spectrahedron in coordinates A1, A2, given by this linear matrix inequality over here. So that's a spectrahedron that I can associate with every complex d by d matrix, and it's in the plane. Now the theorem says, from 1951, that's essentially when Kippenhahn got his PhD, is that this is really convex polar of the numerical range of A. So what does that mean? So this is just the definition of taking the polar. It's a bidual operation. So if you take the polar twice, you get the set itself anyway. So the polar is by definition. So this is the polar of the spectrahedron S of A is by definition all vectors in R2 that make inner product at least -1 with every point of SA. So these are the normal vectors, even finally these are supporting hyperplanes. These are half spaces in R2 that contain the set S of A in one side, right? U comma A less than or equal to -1 defines a half space in R2. U comma A equal -1 is a line, and we look at everything on one side of the line. And we are saying S of A is completely contained in this one half of the plane. Okay, so not only are they polar duals of each other, that's very easy to see actually. That's general convex geometry. If one thing is a projection of a cone, then the dual is a slice of the cone. So that is not so hard to see. We defined it here, S of A as a slice of the cone of Hermitian matrices, and we have seen before that W of A is a projection of the cone of Hermitian PSD matrices, so this is general duality of convex sets. It's not hard to see, so the point of the theorem is really the second part. You can get the numerical range, you can get W of A by taking the convex hull of all points that lie on the so-called dual curve of P, right? So I have this polynomial. The zero set of the polynomial P defines a curve in the plane in P2. And there's a notion that I will explain on the next slide called dual curve. You associate another curve to this one. And the convex hull of this other curve, more precisely, you have to be a little careful about affine versus projective. So you have to look at these points, the sort of finite points on this dual curve with respect to this x0 variable, right? That's a homogenizing variable, plays a special role. And if you take the convex hull of all of the points on that other curve that I'm about to define, then you get the numerical range back. This, I think, Kippenhahn called the boundary defining curve, something like this. So let me tell you about a dual curve. That's a construction in projective algebraic geometry. So here I renamed the polynomial f. So let C be a curve defined. So that's zero set of a polynomial, of a homogeneous polynomial in the projective plane. Suppose this is irreducible. So this is, if you don't know what it means, it's a technical condition to make what I'm about to say true, but it's not the most important condition in the setup. So it means that the polynomial f does not factor. So what do I do? So to form the dual curve, I take the set of points u0, u1, u2 in P2. I collect all of the points such that this line is in the same projective plane as my curve, right? Here I have coordinates x0, x1, x2 in the plane for f. So if I fix these coefficients, these define a line in the plane where the curve C lives, and I want this line to be tangent to the curve at some regular point. So in fact, that means that this point that I've chosen, u0, u1, u2, is collinear to the gradient of f at this point, at some point that lies on the curve. So for instance, if you do this for the circle, so this is the equation of the circle. If you put x0 equal to 1, you just get the Euclidean circle in R2, for example, as the zero set of this polynomial. Then you get the dual curve. You take the gradient at every point. That's what I did here. So these entries are the gradients. So I want u0 to be 2x0, I want u1 to be minus 2x1, and I want u2 to be minus 2x2. But of course, I have the condition that the x's lie on the curve. So you can compute what this is in terms of the u's. Turns out that it's also the circle. So the circle is self-dual with respect to this duality notion for projective curves. So this whole Kippenhahn story, we'll do this for hyperbolic curves. So Daniel mentioned the Helton-Winikoff theorem. So every hyperbolic curve is in fact the boundary of a spectrohedron, right? It's the it has a determinantal representation, a positive definite one. And that's sort of the context of the numerical range, but we're going to generalize to hyperbolicity in higher dimension as well. And in higher dimension, we don't know that spectrohedra and hyperbolicity cones are the same. So we're going to set this up now in the hyperbolic context. So for any Hermitian matrices, for example, real part of A and imaginary part of A, that was our context before, we form this hyperbolic polynomial, which is hyperbolic with respect to 1, 0, 0, because at this point, 1, 0, 0, we get a positive definite Hermitian matrix here, if we plug in to this linear matrix. Okay, so this means all roots are real. I guess Daniel explained that this is because we essentially get the characteristic polynomial of a Hermitian matrix if we restrict to a line like this. So here we have a hyperbolic curve. So this is an example of a sextic, a hyperbolic sextic. We have 6 roots along a line through the interior of the hyperbolicity cone, which here in this picture is called lambda plus. That's Renneger's notation. So for our curve, or for the example where I showed you the numerical range before, which was this matrix A, I have formed real and imaginary part, and here is this determinantal polynomial. that we form in this example, and this defines this curve that I've drawn here. So what is the dual curve in this example? Here's a picture of the dual curve. And you know, I've computed this with a computer algebra system. Its equation is already fairly not so nice. It's a fairly big equation. It's a curve of degree 12. It has genus 3 if you care about such things. And it's therefore highly singular, as we can see, right? It has these. My cursor doesn't show always if I want to. It has these singularities and also maybe more severely these here. These are different. And I'll discuss on the next slide what they are. So it's a classical result. These things, they're called Plücker formulas. So Plücker was not the only one, but he studied duality of plane curves, and he observed all of these things on this slide, for example. So if you have a plane curve of degree d, suppose it's a smooth curve, like in our example here. This is a smooth quartic curve. If you form the dual curve, you get a curve of degree d times d minus 1. So we started with a curve of degree 4 over here, so we got that it was smooth. So the dual curve has degree 12 as predicted by this formula. And if the curve is generic, I don't want to get into what this means exactly, but this curve here, for example, is generic, then the dual curve will have two types of possible singularities. And we see the two types here. So there are nodes. They correspond to bitangent lines. So such a node here corresponds to a line to something like this. To a line that is tangent at 2 points. It's a bitangent line. And a point like this, out here, this is a cusp. So here the curve folds in on it and sort of ends at the singularity. This corresponds to an inflection line. So an inflection line is always very hard to draw. So it's a tangent line where the curve sort of switches sides. So here for this yellow line, the curve remains on the same side as the tangent line. It sort of becomes tangent to the line and then walks back. But in other points, like for instance, I'll try. So here's a flex point down here. So something like this, there's a tangent here where the curve sort of switches side. It's like the graph of y equal x cubed, right? The x-axis is a flex line to the graph of y equal x cubed because the curve switches to the other side. It's a point of multiplicity. So there are 1, 2, 3, 4, 5, 6, 7, 8 of these real flex lines. So there's two. So I drew one of them. There's side and then symmetrically. You can see the 8 real flex lines of this picture. So that's sort of classical plane geometry of curves. So what's the problem with Kippenhahn's theorem? Well, let's take it maybe first in the hyperbolic context, which of course is the same as before, as I already said, by the Helton-Winikoff theorem that we know in this case. But in order to generalize, let's maybe state it explicitly one more time. So now I'm given a hyperbolic polynomial and I fix the hyperbolicity direction to be 1, 0, 0. And then I form this hyperbolicity cone. So that's a convex cone. It's like the spectrohedron associated to a linear matrix, or the determinant of a linear matrix. So this is a convex cone and I make it compact, usually at least. So I take an affine section of this cone. And then I take the convex dual, the polar set of this convex set. And then this is the convex hull of the dual curve. That's exactly what the Kippenhahn theorem said for the numerical range. So for the numerical range, this is the spectrohedron S of A, this blue stuff, and then the dual is W of A. So this is the same statement. So the technical problem, if you try to prove this, is not necessarily sort of the smooth points of the dual curve, but the problem is really in the singularities of the dual curve. So what can happen, as you see in this next picture, is that even in the hyperbolic case, you can have isolated singularities in the dual curve. So what does this mean? So this red point here, for example, in the right, this red is a singular point. It's isolated. There's no other real point of the curve anywhere nearby. It's a node of the curve. It corresponds to a bitangent. It corresponds to a real line that is tangent at 2 points to the curve. But these points are not real. They are complex conjugate. So this can happen. So I can have real nodes that are isolated. They correspond to bitangent lines to the hyperbolic curve in a complex conjugate pair of points. And this is really the technical issue. You have to argue that these always lie inside the convex hull of the curve. So as in this picture, they lie in the very center. And there's no red point sort of somewhere out here. If there was a real node out here, then the theorem would be false. But luckily, the theorem is true. But this is the technical issue you have to worry about. You have to worry about the singularities of the dual algebraic object. Okay. So let's maybe now generalize all of this to higher dimension, and we'll run, as we will see, into exactly the problems that I've discussed in the case of curves. So now we call it the joint numerical range because there are more matrices than one. But now the difference is we assume the matrices to be Hermitian to begin with. The numerical range itself was for a complex matrix without any constraints. For the joint numerical range, we assume Hermitian, so we get the numerical range as before, back in the case n equals 2. So only beginning with n equals 3 and more, we actually generalize here. Anyway, so here's the definition of the joint numerical range. We do exactly the same as before. We do x star a I x for every one of these Hermitian matrices, but since we now assume that they are Hermitian, we end up in R to the n and not in C to the n, right? So x is still a complex vector length t and still norm 1. So formally we do exactly the same, but since we assumed Hermitian, we end up in R to the n. So here this is in general not convex anymore. The Toeplitz-Hausdorff theorem is true for n equal 2. In general, it's not true anymore. I think the easiest examples of lowest degree are for n equals 4, but for high enough degree, I think it's also false for n equals 3, but maybe there's some. It's very well studied, it's very well understood. There's a lot of literature that we can find. So of course, the trace trick that we did before still works. We can write x star ax still as the inner product of ai with x. So we can still assume that we can still consider the joint numerical range as the image of a projection of the Hermitian PSD matrices with trace 1 and rank 1. So now if we drop the rank constraint, we take the convex hull upstairs, we then project, so we get the convex hull downstairs because everything is compact. So, but note here, now I have to put convex hull here on the left, which I wanted to point out, but all we see is a circle. Okay, so here the difference is I put convex hull on the left side because I dropped rank 1, the rank 1 constraint here on the right hand side. Okay, and of course we have the same. The convex hull of a projection is the polar of this is the slice. So I've written the convex hull of the joint numerical range as a projection. So dually, the polar body is a spectrahedral set. So here's a spectrahedral representation. I've chosen coordinates nicely so that this works out. So here's the linear matrix inequality, Hermitian linear matrix inequality defining the convex polar of the numerical range, which is the same of the joint numerical range, which is the same as the convex polar of the convex hull of the joint numerical range. And so we're interested in this convex hull business. I want to describe this analogously to Kippenhahn's theorem in this setup. And this works out in the same way. So we have to now introduce this projective notion of duality, which will replace the duality for plane curves. It's a bit more technical. mostly because we don't have the case of a hypersurface anymore, but okay. So here's the general definition of algebraic, so of duality in projective space algebraically. So I start with a projective variety. So it's the zero set of a bunch of homogeneous polynomials in n+1 variables. Also here I have to assume, which I forgot to write, that this creature is irreducible, which is now a more complicated condition than just it doesn't factor. It's a topological condition on the space. Anyway, so for this, I form the dual variety still in the same spirit. I want to capture tangency. For a dual curve, I collected the tangent lines. Now I want to collect tangent hyperplanes. But if I have, say, a curve in 3 space, then the tangent space at the point will be a line. So what I'm going to do is I'm going to collect all hyperplanes in P3 that contain this tangent line. So this is what I wrote down here. So you take all u's in the dual projective space. So this just means you represent a hyperplane in Pn by a normal vector. The normal vector is unique up to scaling, so it's an element of a projective space. That's the dual projective space. So I identify a hyperplane with its normal vector. And then I want to, right, that's what you see here. This is U is the normal vector of a hyperplane in Pn, and what I want is that the tangent space is contained in this hyperplane at a regular point. And then you have to take the closure of this to get the dual variety. Okay, I guess the definition makes sense even if this thing is not irreducible, but in the irreducible case, as one expects of a duality, you have a biduality statement. If you do this operation twice, you end up with the variety that you started with. So that's a nice and non-trivial theorem in this context. And similarly for curves, you know, in sort of the most generic cases, some things are known. So if V is a generic hypersurface, so if it's defined by just one polynomial that you pick at random, then we know the degree. Then the dual thing will also be a hypersurface. It's in fact the image of the Gauss map. And its degree is going to be analogous to the case of curves. It will only depend on the degree of this polynomial that you sampled, and it's going to be d times d minus 1 to the n minus 1. So for n equals 2, we recover the formula that we saw for a curve. But the things we care about, you know, like hyperbolic polynomials or even better determinants of linear matrices, they tend to be very, very, very non-generic. So these formulas don't apply in the cases that we care about. So for example, if you take the dual variety, you take the set of all matrices that are singular in the space of symmetric d by d matrices. So that's the zero set of the determinant inside this space of symmetric d by d matrices, and you can take the dual variety. You know, okay, formally you have to projectivize, but essentially you can take the dual variety, and what you get out are exactly the matrices of rank 1. So why is that? So roughly because the tangent space, if you sit at a matrix that has co-rank 1, that has a one-dimensional kernel, then it's a smooth point of the determinant, and the normal of the tangent hyperplane is exactly given by the rank 1 matrix coming from an element in the kernel. And that's exactly how you get all rank 1 matrices as hyperplanes that are tangent to the determinant. So that's a relatively simple computation. But of course, this is not a hypersurface, right? It has dimension d minus 1, projectively speaking, but it lives in a d plus 1 choose 2 minus 1 dimensional space, so it's very far away from being a hypersurface. And its degree is also not d times d minus 1 to the n minus 1, but some other number. Okay, so what is this duality? So many of you know the elliptope and like it very much. For the algebraic geometer, this is known as the Cayley cubic, and that's the creature on the left-hand side. So for us, in some sense, that is more natural in the dual space. We have the spectrahedra in the dual space, and the numerical range itself is the polar. That's the one that's for us the primal object. So the dual is for us in the primal projective space. Okay, so here's the elliptope. It's the convex, so it's only this thing in the interior, right? So these ears here, these 4 ears that you see is where the determinant is 0, but the elliptope itself is just sort of the convex region bounded by this red interior blob. Okay, and here algebraically, this is the dual object. This is called the Roman surface. It's the dual surface to the Cayley cubic. And it has, which is a bit hard to see in this picture, it has 3 lines also. So there's a line sticking out here and here. There's a line here. And then one coming out at us. It's hard to draw right here at this point that I want to show you. Yeah, there's a line sticking out of the screen plane. So if we take the convex hull of all of these points, this includes these 3 lines, so we get all of our 3. That's certainly not what we want. This is not the polar of the elliptope. So how can we fix this? That is sort of the naive generalization of Kippenhahn's theorem would be, well, just take the convex hull of everything on this dual surface, and you get the polar set. Right? You get the joint numerical range, which is polar to this hyperbolic region. That doesn't work. There's another example. So Chen and Nakazato are more applied mathematicians who care very much about this numerical and joint numerical range. And so they thought about this problem. They thought about ways to generalize Kippenhahn's theorem to higher dimensions. And then they also observed the same problem that I just talked about in a different example. So here you only see the dual surface, and again there's this problem. There's this red line sticking out of the surface, so if you take the convex hull, you get too much. You get a half space here in this example, and it's not what you want. You want the convex hull of all of the blue things without the red. That's the correct thing. And that's actually also the theorem that we proved in the hyperbolic case. So suppose you have a hyperbolic polynomial now in many variables. So the joint numerical range case is the spectrahedral special case of this theorem, which might not be a special case depending on the generalized Lex conjecture, but so this only uses the hyperbolicity and facts we know about hyperbolic polynomials. It doesn't use the determinantal representations, which may or may not exist. So you start with a hyperbolic polynomial, and the way I phrased it, I'm not careful about algebraic duality, so you should assume irreducible, but that's just to make the statement easier. We have a version, of course, where you can, where you don't need this assumption. And we suppose that it's hyperbolic, so we choose coordinates so that this hyperbolicity direction is the first unit vector, canonical basis vector, and we look at the projective variety defined by this. This is now in Pn, and we take the dual variety as explained before. Then we're interested in this object. So this is sort of the analog of S of A. You take the hyperbolicity cone of this polynomial with respect to this direction E, and you take an affine section of it. Then you take the convex dual, so this should be W of A, and this W of A is the convex hull of the dual variety in the following careful sense. So you only take, well, as before, you only take the points that are finite with respect to this homogenizing variable, so you only look at points where U1 is equal to 1. But then you don't take all of the points on the dual variety, but only those where the dual variety is smooth. Okay, and then you take the convex hull of that, so you don't, in general, get a closed set, but the polar is always closed, so you then close it up, and then you get the right thing. And sort of the special thing that happens for curves is that you can get rid, by studying the singularities carefully, you can get rid of this extra condition that you only look at the regular points. So that's what is needed to be able to generalize to higher dimensions. So, and as I said before, the direct generalization of Kippenhahn's theorem, which only deals in some sense with the determinantal case, is this following fact. So the convex hull of the joint numerical range of Hermitian matrices is always the closure of the non-singular and real part of the dual variety of the hyperbolic hypersurface that you get from the matrices. So this is the case where this hyperbolic polynomial has a Hermitian determinantal representation. All right, so this is the correct way to generalize Kippenhahn's theorem to the joint numerical range of Hermitian matrices, and that's all I wanted to tell you today. Thank you very much.